Hi, welcome to this lesson on structural equation modeling. This lesson will be your first step into statistical modeling, which deviates from what we've done previously. Our previous lessons mainly revolved around one or more independent variables affecting one dependent variable. However, our world is often much more complicated than that. Dependent variables can influence other dependent variables, or have an interaction effect with certain independent variables. To model this complexity, structural equation modeling, or SEM, can be very useful. That will be the topic of this lesson. Let's get started. What exactly is structural equation modeling? Well, as I said in the introduction, it's unlike what we did previously. When we did a t-test or an ANOVA or even a regression analysis, these analyses were single approaches to address research questions. SEM is better thought of as a general modeling framework that integrates a number of different multivariate techniques, such as factor analysis, path analysis, regression modeling, and more. It's particularly useful in situations where the key factors you want to analyze are complex and multifaceted. It's most often used as a path analysis using latent variables. Latent variables are variables which we cannot directly measure, which is quite common in the world of social sciences. Think of concepts such as intelligence, proactiveness, and happiness. It's impossible to directly measure these concepts, as we don't have a spectrometer to measure that the happiness of person 8 is a 7.8 out of 10, for instance. No, we can only measure them in other observable behaviors that we think are related to these underlying latent constructs. For instance, we measure intelligence through an IQ test. Now, IQ tests are not a one-on-one measurement of intelligence, as there will always be some variability. IQ is an indication of intelligence, and on top of that, perhaps the participant was feeling tired, got distracted thinking about the weekend, or the questionnaire design was flawed. These are all factors which we're not interested in. So the variability in the IQ score that we observed of a dozen people will be, to some extent, due to the latent construct intelligence, but some of the variability will also be due to other factors, which we call error. You already learned quite a bit about errors in the lesson on linear regression, so I won't go too much in depth. But to repeat what I said then, the data in our model can be characterized by the following formula. Data equals model plus error. We can also use some other words for this. Observed score is true score plus error. What we want to achieve with SEM is to minimize this error. This will allow us to more accurately predict what we want to predict. Unfortunately, due to the fact that we only have one indicator for the latent variable intelligence, we can't exactly know what part of our observed score is due to error. In our formula of observed score equals true score plus error, we only know for sure one score, and that is the observed score. The true score and error are both unknown pieces of information, so we can't separate them from each other. However, when we have multiple indicators of our latent construct, then we can start to estimate the quantities of the true score and error for each indicator. We can represent this by showing you a common factor model. Here, we have three measured variables. These all measure intelligence to some degree. So for instance, a verbal test, a numerical test, and an abstract reasoning test. These three indicators are all of the same underlying latent variable, intelligence. Now, because they measure the same thing, we would generally expect these variables to be correlated in our population. That's what the double-headed arrows indicate. As you can see, all of these indicators have some type of error associated with them, as there's always an element of chance or luck involved when filling out these types of questionnaires. The latent variable, intelligence, has a causal effect on all of these indicators. The more intelligent you are, the higher your score will be on all three indicators. The latent variable can be seen as our true score in the formula of x is true score plus error. So now you know what latent variables are, but what is a path analysis? A key feature of path analysis is that the model that you're wanting to fit to the data is represented diagrammatically, rather than in the form of equations. The equations would be overwhelming and difficult to understand, but putting the variables in a diagram will help with the visual aspect and enable you to understand the question better. The path analysis allows us to focus on not just direct effects, but also indirect effects, interaction effects, and total effect. So, for HR questions where a simple linear model won't work, where we're estimating the effects of some set of predictive variables on an outcome, like turnover or performance, we're interested in the pathways between multiple independent variables and possibly multiple dependent variables. So in this slide, you see a path analysis and its standardized notation. At the top is the latent variable, such as IQ, which is presented as an ellipse. Next, we have an observed variable, such as an abstract reasoning test, which is presented as a rectangle. The error is shown as a small circle. The covariance path, where we're specifying that two variables in the model are related or correlated with one another, would be presented as a curved double-headed arrow. This doesn't show a causal relationship, just a correlation between the two variables. A causal relationship is shown by a single-headed straight arrow. So here are a few examples of some simple path diagrams. In this simple diagram, we can see that the latent variable x has a causal effect on the observed variable y, with the error e also influencing the observed variable. This is essentially a simple linear regression model. Now the next example is a multiple linear regression model, where the two variables being observed are correlated with one another. Now, as I mentioned earlier, one of the great things about path diagrams and structural equation modeling is the study of direct and indirect effects. Here, you have a diagram that has a complex relationship between these variables. Y has a direct effect on x1 and x2, and x1 also has a direct effect on x2, so we have an indirect effect of y on x2 through x1. We can characterize these effects as beta 1 to beta 3. So here, beta 1 represents the direct effect of y on x1, beta 2 is the direct effect of y on x2, and beta 3 is the direct effect of x1 on x2. The indirect effect is beta 1 times beta 3. So now we can also calculate the total effect of y on x2, which is the sum of beta 2 and the product of beta 1 and beta 3. Here's an example of a structural equation model in real life. We have two latent variables, intelligence and academic performance. Intelligence has a causal relationship with academic performance of 0.8. Intelligence has a fixed scale of 1, noted by the @1 above it, to provide scale to the dimensions of this model. Next, we see that intelligence has a causal relationship with multiple observable variables. Scale 1 0.7, scale 2 is 0.64, scale 3 is 0.73, and scale 4 is 0.84. Each of these variables has an error associated with them. Furthermore, we have academic performance, which has a causal relationship with three observable variables, namely the SAT score of 0.98, high school GPA of 25, and ACT score of 0.87. All of these variables, including academic performance, have an error associated with them. It is hard to put all of these variables in one multiple regression model, but through the use of SEM, we can model and estimate each of these variables' strength on each other and on the latent variables that have a causal relationship with them. So that gives a very brief overview of both latent variables and path analysis to understand what you're doing with structural equation modeling. Don't despair if you don't understand everything yet, or if you struggle to apply a structural equation model. It is a highly complicated technique that is usually only taught at PhD level. That's it for this lesson. In this lesson, you learned about structural equation modeling. You learned that its main use is to analyze complex relationships between variables. Next, you learned about latent variables, which are complex constructs which cannot be directly observed, such as intelligence or happiness. And you learned about pathway analysis, which is the way we represent the data diagrammatically. That's it for Module 4. Enjoy the bonus material and best of luck in your people analytics journey.